Why is the universe expanding faster and faster? Before there were stars, galaxies, or even time itself, there was nothing. No sound, no light, no atoms, not even space. Then, in a moment that really defies imagination, everything began. About 13.8 billion years ago, the universe suddenly came into existence in an event we now call the Big Bang. But calling it an explosion is actually a bit misleading. The Big Bang didn't happen in space. It was the expansion of space itself. There was no outside for it to expand into. Space, time, energy, and the laws of physics all emerged together in an instant. From that singular moment, the universe began to stretch, expand, and evolve, and it has never stopped. During the very first fraction of a second, less than 1/10,000 trillionth of a second after the Big Bang, the universe experienced something truly extraordinary: cosmic inflation. This was a period of hyper-rapid expansion when the universe grew exponentially, doubling in size countless times in an instant. In less than a trillionth of a second, it went from smaller than a subatomic particle to the size of an entire galaxy. This happened faster than the speed of light, but that doesn't break Einstein's laws, because it wasn't matter moving through space. It was space itself expanding. The energy driving this expansion was vast, and the young universe was unimaginably hot. Temperatures around 10 to the 32nd power Kelvin, a heat so intense that matter as we know it couldn't exist. Everything was pure energy, a seething quantum foam of particles and antiparticles appearing and annihilating in an instant. Then, as the expansion continued, the universe began to cool. Within the first microseconds, energy condensed into fundamental particles: quarks, gluons, and electrons. Quarks combined to form protons and neutrons, and for the first time, the building blocks of atoms were born. In the first 3 minutes, the universe's temperature had fallen enough for these particles to fuse into the first atomic nuclei. This process, known as Big Bang nucleosynthesis, created mostly hydrogen, about 75%, and helium, about 25%, with just trace amounts of lithium. These light elements would later become the fuel for the first stars, the stars that would forge everything else: carbon, oxygen, iron, and even the elements that make up our bodies. At this point, the universe was still completely dark. There were no stars, no galaxies, only a dense, hot fog of particles and radiation, a cosmic soup. Light couldn't travel freely because it kept bouncing off free electrons. The universe was opaque. This era lasted for about 380,000 years. Then, as the universe cooled to about 3000 Kelvin, a dramatic change occurred. Electrons began to combine with atomic nuclei to form neutral atoms in a process called recombination. For the first time, light could move freely through space. The universe became transparent, and that ancient light still travels through the cosmos today. We can still detect it. It's called the Cosmic Microwave Background Radiation, or CMB. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is like a baby picture of the universe. The oldest light, we can see a faint glow that fills the entire sky. It shows us what the universe looked like just 380,000 years after its birth. Tiny variations in this light, only a few millionths of a degree, tell us where matter was slightly denser or thinner. Those small differences were the seeds that gravity would later amplify to form galaxies, stars, and planets. As the universe continued to expand, gravity began to take over. The denser regions started to collapse under their own weight, forming the first stars around 100 to 200 million years after the Big Bang. These stars were enormous, hundreds of times more massive than our Sun, and they burned hot and fast, flooding the universe with light. When they died in massive explosions called supernovae, they scattered the first heavy elements into space. Those elements would later form new stars, planets, and eventually, life itself. Over billions of years, galaxies formed, vast islands of stars bound together by gravity. The universe had entered its grand architectural phase. Astronomers once thought this expansion, triggered by the Big Bang, would gradually slow down. It made perfect sense. Gravity, the great cosmic glue, should pull everything together. For decades, scientists debated the universe's fate. Would it eventually stop expanding and collapse in a big crunch? Would it expand forever, but at a decreasing rate? The universe's destiny seemed to depend entirely on how much matter it contained. If there was enough matter, gravity would eventually win, pulling everything back. If not, expansion would continue but slowly, forever stretching the cosmos thinner and colder. But then came a discovery that changed everything. A discovery that, honestly, stunned astronomers and rewrote the story of the cosmos. In the late 1990s, two teams of researchers, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, set out to measure how fast the universe's expansion was slowing down. They used Type Ia supernovae, special kinds of exploding stars that always reach the same brightness before fading. These standard candles allow astronomers to measure distances across the cosmos with remarkable precision. But when they looked at supernovae in very distant galaxies, meaning they were looking billions of years into the past, they found something that defied all logic. Those supernovae were dimmer than expected. That meant they were farther away than they should be, given the rate of expansion predicted by existing models. At first, this didn't make sense. If the universe was slowing down, distant galaxies should be closer than the data showed. But the only explanation that fit the observations was astonishing. The expansion of the universe was not slowing down at all. It was speeding up. Something was pushing galaxies apart, faster and faster. Something completely invisible. Something that didn't emit light or interact with matter. Scientists had no idea what it was, so they gave it a name that captured both its mystery and its power: dark energy. This discovery shook the foundations of cosmology. It meant that roughly 68% of the universe is made of this unknown energy, while dark matter, another invisible component, makes up about 27%, and everything we can see, stars, planets, and galaxies, accounts for less than 5%. The universe we know is only a small fraction of what actually exists. The discovery of the universe's accelerating expansion earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. And it opened an entirely new chapter in our understanding of the cosmos. It told us that the story of creation is not just about how the universe began, but about how it continues to evolve, faster, stranger, and more mysterious than anyone ever imagined. By the late 20th century, astronomers believed they had a fairly good understanding of how the universe worked. Ever since Edwin Hubble's discovery in 1929 that galaxies were moving away from each other, revealing that the universe was expanding, scientists assumed this expansion must be slowing down over time. Gravity, after all, is the great cosmic brake. Every galaxy, every star, every atom with mass pulls on every other, trying to bring the universe back together. So, by the 1990s, the question seemed straightforward. How fast is the expansion slowing? Not if, but by how much? The universe's fate depended on that answer. Would gravity eventually halt the expansion and pull everything back in a big crunch, collapsing the universe into itself? Or would expansion continue forever, leaving galaxies to drift endlessly apart in a cold, lonely, big freeze? To find out, two independent teams of scientists began one of the most ambitious astronomical projects ever attempted. The first was the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. The second was the High Z Supernova Search Team, led by Brian Schmidt from Australia and Adam Rees from Johns Hopkins University. Despite being competitors, both teams shared the same goal: to measure how the universe's expansion rate had changed over time. But measuring the speed of the universe across billions of years is no easy task. They needed something precise, something that could serve as a cosmic yardstick. That something turned out to be a special type of exploding star known as a Type Ia supernova. Type Ia supernovae are extraordinary. They occur when a white dwarf star, the remnant core of a dead star roughly the size of Earth, steals matter from a nearby companion star. When the white dwarf reaches a critical mass, about 1.4 times the mass of our Sun, it can no longer support itself against gravity and undergoes a catastrophic thermonuclear explosion. The result is a blinding flash that briefly outshines an entire galaxy. What makes Type Ia supernovae so valuable to astronomers is their predictability. Every explosion releases roughly the same amount of energy and reaches nearly the same peak brightness. This makes them perfect standard candles, objects of known luminosity. By comparing how bright a supernova appears from Earth to how bright it should be, scientists can determine its distance with remarkable accuracy. The dimmer the supernova appears, the farther away it must be. Using the most advanced telescopes of the time, including those at Cerro Tololo Inter-American Observatory in Chile and the Keck Observatory in Hawaii, both teams searched the sky for these rare cosmic beacons. They scanned thousands of distant galaxies, capturing faint points of light that represented explosions that had occurred billions of years ago when the universe was much younger. When they finally analyzed the data, what they found was, well, completely unexpected. The distant supernova, the ones whose light had traveled across most of the observable universe, were dimmer than their models predicted. That meant they were farther away than they should have been if the universe's expansion had been slowing down. The only explanation that made sense was, honestly, astonishing. The expansion of the universe wasn't decelerating, it was accelerating. The universe, it turned out, wasn't acting like a ball thrown upward and slowing under gravity. Instead, it was acting as if some invisible hand were pushing it outward, faster and faster, stretching space itself with increasing speed. It was as if the cosmic engine had found a new source of fuel, one that no one had ever seen or imagined. When these results were published in 1998, the scientific world was, well, stunned. For decades, cosmologists had assumed gravity would eventually slow cosmic expansion. But now, the evidence showed the exact opposite. The universe was not only expanding, but doing so faster with time. At first, scientists were skeptical. The idea seemed absurd. Some thought there must be an error in the data. Maybe the distant supernovae were dimmer because of dust, or perhaps they were somehow different from nearby ones. But after careful reanalysis, more observations, and independent confirmations from other teams and space telescopes, the result held firm. The acceleration was real. This was one of the most profound discoveries in the history of science. It meant that the universe is dominated by something entirely unknown, a mysterious energy that permeates all of space and counteracts gravity on the largest scales. To explain it, cosmologists revived an idea first proposed, and later rejected, by Albert Einstein himself, the cosmological constant. Einstein had introduced it in 1917 to keep the universe static before the expansion was discovered. He later called it his greatest blunder, but now his so-called blunder seemed to describe exactly what was happening. In recognition of this revolutionary discovery, Saul Perlmutter, Brian Schmidt, and Adam Riess were awarded the 2011 Nobel Prize in Physics. Their work revealed that the universe we live in is not what it appears to be. Roughly 68% of it consists of this mysterious force, now called dark energy, the agent responsible for driving galaxies apart faster and faster. But the discovery, as groundbreaking as it was, raised even deeper questions. What exactly is dark energy? Is it a property of space itself, a constant energy embedded in the vacuum? Or is it something dynamic, an evolving field that changes over time? Could it even point to flaws in our understanding of gravity? The answers remain unknown. What began as a simple question, how fast is the universe slowing down, became the greatest mystery in modern cosmology. The discovery that the universe is accelerating not only changed what we know about the cosmos, it changed what we know about the laws of physics themselves. To explain this strange and unstoppable acceleration of the universe, scientists turn to one of the most mysterious ideas in modern cosmology: dark energy. Imagine this: everything we see around us, stars, galaxies, planets, even the atoms in your body, makes up just a tiny fraction of the cosmos. In fact, normal matter, the kind that emits or reflects light, accounts for only about 5% of the universe. The rest is invisible. About 27% is dark matter, a mysterious form that doesn't glow but whose gravity helps hold galaxies together. But the real enigma, the dominant force shaping the fate of the universe, is dark energy, making up a staggering 68% of everything that exists. But what exactly is dark energy? That's the great cosmic mystery. It doesn't shine, it doesn't absorb or scatter light, it doesn't interact with matter in any way we can measure. And yet, its influence can be seen everywhere, pushing galaxies apart, stretching the very fabric of space itself, and accelerating the expansion of the universe. It's as if space isn't empty at all, but filled with an invisible pressure that grows stronger as the universe grows larger. The leading explanation for dark energy traces back to none other than Albert Einstein. In 1917, when he formulated his famous general theory of relativity, his equations predicted that the universe couldn't remain static. It had to either expand or contract under its own gravity. But at the time, everyone, including Einstein, believed the universe was eternal and unchanging. So, to make his equations fit this assumption, Einstein introduced an extra term called the cosmological constant. This mysterious constant acted like a repulsive force that perfectly balanced gravity, keeping the universe stable and motionless. However, years later, when Edwin Hubble discovered that the universe was actually expanding, Einstein realized that his fix was unnecessary and called it his biggest blunder. But here's the irony: that so-called mistake may have been one of the greatest insights in scientific history. Because today, more than a century later, the cosmological constant has returned, not as an error, but as the leading explanation for dark energy. According to modern physics, empty space itself has energy. A kind of vacuum energy that doesn't disappear even when all matter and radiation are removed. This energy is uniform, constant, and woven into the fabric of space-time. And as the universe expands, more space is created, meaning more vacuum energy, more dark energy, and thus an ever faster expansion. In other words, the universe is not just stretching. It's being driven to expand faster and faster by an invisible, unstoppable energy that fills every corner of existence. What once seemed like a quiet, empty void is, in truth, the most powerful force in the cosmos, one that could determine the ultimate fate of everything. To understand how the universe expands, imagine something simple: a balloon. Now picture tiny dots drawn all over its surface. As you blow air into it, the balloon stretches, and every dot moves away from every other dot. But notice something fascinating. The farther two dots are apart, the faster they separate. This is exactly how our universe behaves on a cosmic scale. Galaxies aren't flying through space. Space itself is expanding, carrying galaxies along with it. This relationship between distance and velocity was first discovered in 1929 by American astronomer Edwin Hubble. By studying the light from distant galaxies, he found that their light was stretched toward the red end of the spectrum, what we now call redshift. The farther away a galaxy was, the greater its redshift, meaning it was moving away faster. This remarkable observation led to Hubble's law, the mathematical rule that defines the universe's expansion. The farther a galaxy is, the faster it recedes from us. The speed of this expansion is described by a number called the Hubble constant, a cosmic yardstick that tells us how fast the universe is growing per unit distance. For example, a galaxy 1 megaparsec, which is about 3.26 million light-years away, is receding at roughly 70 kilometers per second. But here's where the story takes a mysterious turn, because we don't actually agree on what that exact number should be. Over the past decade, astronomers have measured the Hubble constant using two very different cosmic yardsticks. And the results don't match. When we look at nearby galaxies and type Ia supernovae, which act as standard candles, we find a value around 73 kilometers per second per megaparsec. But when we peer deep into the past, at the cosmic microwave background, the faint afterglow of the Big Bang, measured by the Planck satellite, we get a lower value, around 67 kilometers per second per megaparsec. This discrepancy might sound small, but in cosmology, it's enormous. It's called the Hubble tension, and it has become one of the biggest unsolved puzzles in modern astrophysics. Both sets of measurements are incredibly precise, yet they point to different answers. That means either one of our measurements is missing something, or the universe itself is trying to tell us that our physics is incomplete. So what could explain this cosmic mismatch? Some scientists suggest that dark energy might not be constant after all. Perhaps it evolves over time, growing stronger or weaker as the universe expands. Others suspect the presence of new, undiscovered particles, maybe dark radiation or a new species of neutrino influencing the early universe's behavior. There are also those who think the problem lies deeper, within Einstein's own equations, suggesting we may need a new theory of gravity altogether. In essence, this tension isn't just a math problem, it's a signpost. It could be pointing us toward a new era of physics, one that expands our understanding of the cosmos just as profoundly as Einstein's theories did a century ago. The universe, it seems, is still keeping some of its greatest secrets hidden between the stars. And, well, the Hubble tension might be our next great clue to unlocking them. When we gaze up at the night sky, we're not just looking across space. We're looking back in time. Every twinkle of starlight is a message from the past. The light that reaches your eyes tonight may have begun its journey millions, even billions of years ago. The farther we look, the older the universe we see. When astronomers peer deep into the cosmos with the most powerful telescopes, the Hubble Space Telescope, the James Webb Space Telescope, and the Euclid mission, they are essentially time travelers, witnessing the history of the universe unfold across billions of years. With these cosmic eyes, scientists have traced the grand story of how galaxies came to be. In the earliest chapters, only a few 100 million years after the Big Bang, the universe was a glowing fog of hydrogen and helium. Tiny fluctuations in density, barely noticeable, slowly grew under gravity's pull, forming the first stars, then clusters, then entire galaxies. Over time, as space itself expanded, galaxies drifted farther apart, yet their internal structures, spiral arms, star nurseries, supermassive black holes, continued to evolve. But as astronomers looked deeper and deeper into space, they noticed something astonishing. Not only were galaxies moving away, they were doing so faster the farther they were. And this wasn't just about the galaxies themselves moving. It was space itself that was stretching. The very fabric of the cosmos was expanding like an invisible elastic sheet being pulled from all directions. On small scales, within galaxies, or even within galaxy clusters, gravity still reigns supreme, binding stars and matter together. But across vast cosmic distances, another force takes over: dark energy. Its repulsive effect pushes everything apart, overpowering gravity on the largest scales imaginable. The result? The great cosmic web of galaxies, once tightly knit by gravity, is slowly unraveling. Now, imagine the far future, billions or even trillions of years from now. The Milky Way and Andromeda Galaxy will have merged into a single giant elliptical galaxy, surrounded by a handful of small companions, our local group. But beyond this small island of stars, everything else, all the distant galaxies we see today, will drift farther and farther away. They'll move so fast that their light will never be able to reach us again. This moment marks what cosmologists call the cosmic event horizon, the ultimate limit of what we can ever see or know. Beyond this horizon, space expands faster than light can travel, trapping distant galaxies forever beyond our reach. To future astronomers living in that distant epoch, the universe will appear dark and empty. They will see only the merged remnant of our local galaxies, unaware that beyond their cosmic shores once lay billions upon billions of galaxies, now lost to eternity. It's a haunting thought that one day the grand story of the cosmos, the evidence of its origins, might vanish from view entirely. Yet, it also reminds us how precious this moment in cosmic history truly is. We live at a time when we can still see the universe in its vast glory, from the birth of the first stars to the edge of time itself. The light reaching us today is not just illumination, it's a whisper from the ancient universe, telling us where we came from, and perhaps hinting at where we're going. What will ultimately happen to our universe if this cosmic expansion continues to accelerate? It's one of the most profound questions in all of science, and the answer depends entirely on the true nature of dark energy. Since we still don't know what dark energy actually is or how it behaves, cosmologists have imagined several possible endings for the universe. Each one paints a vastly different picture of the distant future, from a slow, cold fading to a violent cosmic rupture. Let's begin with the most widely accepted scenario. The Big Freeze, also known as the heat death. If dark energy remains constant, neither strengthening nor weakening, the expansion of the universe will continue forever, pushing galaxies farther and farther apart. Over billions of years, new stars will stop forming as galaxies exhaust their gas. The existing stars will burn out one by one, leaving behind only cold remnants, white dwarfs, neutron stars, and black holes scattered across an ever-growing darkness. Trillions of years later, even black holes will evaporate through Hawking radiation, releasing their final whispers of energy into the void. Eventually, the universe will become a vast, frozen desert of faded particles, with no light, no heat, and no structure, a quiet cosmic graveyard. Time will stretch endlessly forward, but nothing new will ever happen again. This is the ultimate thermodynamic equilibrium, the end of all change. But there's another, far more violent possibility: the Big Rip. What if dark energy doesn't stay constant, but instead grows stronger with time? If its repulsive force continues to increase, it could overpower all other forces in the universe. First, galaxy clusters would drift apart. Then, entire galaxies themselves would be torn asunder. Eventually, the very stars, and then the planets orbiting them, would be ripped from their orbits. And in the final, terrifying moments, dark energy's strength would overwhelm even the atomic forces that hold matter together. Atoms would literally be torn apart, and space-time itself would be shredded. The universe wouldn't just end, it would unravel from within. The Big Rip would be the most catastrophic ending imaginable. A cosmic explosion of nothingness that ends everything, everywhere, all at once. And yet, there's a third possibility. The Big Crunch, or its more hopeful version, the Big Bounce. Suppose dark energy isn't permanent. Perhaps it changes sign in the distant future, turning from a repulsive force into an attractive one. If that happens, gravity could eventually slow the expansion and reverse it. The universe would begin to contract, galaxies drawing closer, temperatures rising, and space-time itself folding inward. Everything, stars, planets, even light, would collapse back into a single, infinitely dense point, a singularity, much like the one from which the universe was born. And from that fiery collapse, perhaps another Big Bang could emerge, a rebirth of the cosmos in an endless cycle of expansion and contraction, a universe that dies only to live again. Each of these scenarios, the Big Freeze, the Big Rip, the Big Crunch, depends on what dark energy truly is and how it behaves over time. Right now, our telescopes can measure its effects, but not its nature. It could be a simple cosmological constant, a field that evolves, or something entirely unknown, a new force or property of space-time itself. What we do know is this: the fate of the universe is written in the language of dark energy, a language we are only beginning to decipher. Whether our cosmos ends in ice, fire, or eternal rebirth, the mystery of dark energy will decide the final chapter of everything, from the smallest atom to the largest galaxy, and even the fabric of space-time itself. To truly understand why the universe is expanding faster and faster, scientists are now turning their gaze toward the future, building a new generation of observatories designed to unravel the mystery of dark energy itself. Around the world, engineers and astronomers are constructing some of the most advanced instruments ever conceived, machines that will look deeper into space and further back in time than any before. One of the most ambitious of these is the Vera C. Rubin Observatory, perched high in the Chilean Andes. Beginning its grand project, the Legacy Survey of Space and Time, or LSST, it will capture a vast cinematic record of the sky, photographing the entire visible universe every few nights. Over 10 years, it will observe billions of galaxies, tracking how their positions and movements evolve over cosmic time. This immense data set will allow scientists to map the subtle ways in which space itself has stretched and grown, giving us an evolving picture of how cosmic expansion has changed through billions of years. Meanwhile, orbiting far above Earth, the Euclid mission, launched by the European Space Agency in 2023, is already scanning the heavens with astonishing precision. Euclid's mission is to chart the geometry of the universe, measuring how light from distant galaxies bends and warps as it travels through space. This bending, known as gravitational lensing, acts as a cosmic fingerprint of dark matter and dark energy. By studying millions of galaxies spread across 10 billion light-years, Euclid will reveal how the tug of gravity and the push of dark energy have sculpted the universe's grand structure, the cosmic web that binds galaxies together. And soon another eye will open to the cosmos, NASA's Nancy Grace Roman Space Telescope. Often described as the Hubble on steroids, Roman will combine wide-field vision with extreme sensitivity, allowing scientists to probe deeper into the nature of cosmic acceleration. Its observations will help determine whether dark energy is truly constant, or if it's evolving over time, changing the fate of the universe itself. Yet even as we look forward, the answers may also lie in the oldest light of all, the cosmic microwave background, or CMB, which is the faint afterglow left behind by the Big Bang. This radiation, discovered way back in 1965, has actually been traveling through the universe for 13.8 billion years, carrying within it a record of the universe's earliest moments. Tiny variations, differences in temperature as small as 1 part in 100,000, reveal how matter and energy were distributed just 380,000 years after the Big Bang. These delicate patterns are like fingerprints from the dawn of time, showing how the seeds of galaxies were planted and how the balance between gravity and expansion began. By comparing these early imprints with modern observations, scientists can trace the entire life story of the cosmos, from its hot, dense beginnings to its vast, accelerating present. Every new telescope, every new measurement brings us one step closer to understanding the invisible force that drives our universe apart, and to answering one of the greatest questions in all of science. Why is the universe expanding faster and faster? Despite all the incredible progress humanity has made, the question still stands. Why is the universe expanding faster and faster? What invisible hand is pushing galaxies apart, reshaping the fabric of space-time itself? Is dark energy simply a built-in property of the vacuum, an intrinsic energy of space that has existed since the dawn of time? Or is it something even more exotic, a dynamic field known as quintessence, that slowly evolves and changes as the universe grows? Could it be that our most trusted theory, Einstein's general relativity, breaks down on the grandest scales, and that gravity itself behaves differently than we've ever imagined? Every new telescope, every experiment, every map of the cosmos brings us closer, yet also deepens the mystery. The more we discover, the more questions unfold. Each answer feels less like an ending and more like a new doorway opening onto the unknown. And that is the very heart of science, not certainty, but the courage to keep asking. Perhaps one day, with the help of future observatories and, a deeper understanding, we will finally uncover what drives this invisible force, the power that decides the fate of the cosmos itself. But until that day comes, we continue to look upward, our instruments pointed toward the stars, our minds filled with questions as vast as the universe we study. The accelerating universe is more than just a mystery of physics. It's, well, a mirror reflecting our own existence. It reminds us of how small we are, and yet how deeply we belong to the grand story unfolding across time and space. We are fleeting, fragile beings on a small blue world. And yet, through science, we've reached across billions of light years to grasp the workings of creation itself. Even as galaxies rush away into the darkness, our curiosity reaches farther still. Because curiosity is the one force that, honestly, truly never stops expanding. And in that endless pursuit, in that eternal quest to understand, lies the most beautiful truth of all. We are part of the universe that's trying to understand itself.